Hey everyone, welcome to 1.3. This is going to be a long one, so let's start off with your trivia question first. What did competitive eaters munch at a 2004 Madison Square Garden event called the Battle to the Bone? Answer at the end of this lesson. We're going to start here with 1.3, evaluating limits analytically, and we're going to talk about properties. We have a lot of properties, lots of theorems. They're fairly straightforward, but we kind of need to get the basis, that way we can move on to when they get a little more complicated in one of the next videos. So, well-behaved functions. They are going to be continuous at C, so like a line, for example. So if this is C, if I plug in C for X, I'm going to get a value right there. We don't have to worry about holes, we don't have to worry about asymptotes, we don't have to worry about anything. We're just going to say, if I plug in C for X, I'm going to get a number. And that's the basis for all of the theorems we are about to do. Alright, so here's theorem 1.1, basic limits. Let B and C be real numbers, and let n be a positive integer. So if I have a limit as x approaches c of just some number, I'm going to get that number. If the limit as x approaches c of x, I'm going to get that c. I'm going to get that number, and if I have x approaches c as x to the nth power, it's going to be c to the nth power. Really, really simple. So it's kind of like evaluating. Remember in Algebra 1 we said evaluate for when x, we evaluate when x is 4. And you'd say, okay, and then plug in 4 for x, and then you get a bunch of answers. That's what we're doing here, right? So I'm going to plug in 2 for every x that I see. I don't see any x's, so this is just going to be 3. Easy. The limit as for x as x approaches 2, well, that's just going to be 2, because as x approaches 2, you're going to get 2. And the last one, the limit as x approaches negative 4 of x squared. Well, what's negative 4 squared? 16. So all we really have to do is plug it in. You get an answer. No problem. All right. So there's the first set of theorems. Remember, you can always pause if you need to. If I'm going too fast, pause it, go back, and you can just copy everything down. Theorem 1.2, properties of limits. Let b and c be real numbers, let n be a positive integer, and let f and g be functions with the following limits. So the limit as x approaches c of some function f of x equals L, which is just a number, and the limit as x approaches c for g of x equals k, another number. So we have a scalar. The limit as x approaches c of b times this function f of x is going to be the same as b times whatever the limit is. Some are different. The limit as x approaches c for f of x plus or minus g of x is going to be L plus or minus k. So if I'm adding the functions, I can just add what their limit is. Product. If I'm multiplying the functions with the limit, I can just multiply what their limit is. For quotient, as x approaches c, if I'm dividing them, this works out as long as g of x is at 0 and as long as k is not 0. Alright? There we go. And then the last one, power. As x approaches c, f of x to the n is just going to be the limit to the nth power. Alright, so here's one example. We're actually going to use sum or difference. Alright, because this is actually two functions, so we can just say this is the same as limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. Alright, so the limit as x approaches 2 of 3 is just going to be 3. And this one, I just plug the 2 in there, and I make sure to do order of operations. 2 squared is 4. 4 times 4 is 16, and I would still add them together. 16 is 19. And I know what you're thinking. You're saying, but Mr. Berman, can't we just put in the 2 here and get the same thing? Yes, you can. I'm just showing you how these theorems work. Alright, so either way will be okay, and that's fine to do. Next, we have theorem 1.3, limits of polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x equals p of c. If you remember when we were first talking about limits or functions, when we talked about functions, we said, let's say we had like f of x equals, let's say, x squared plus 3. And then you said, well, I asked you, what is f of 3? And you said, well, can I just put in this 3 for that x every time I see an x? Yes, you can. That's really what we're looking at, is you're just saying put in a number for x and then evaluate the function. Alright, and that's just a shorthand way of writing it. Alright, if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c does not equal 0, then we can say the limit, this should not be an equal sign right there. The limit as x approaches c of r of c is going to equal p of c over q of c. Now, one of the main reasons why we're going over all these theorems in detail is that sometimes you'll get something like this. Right? You have to include this little thing where it says it's a rational function, blah, 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 such that q of c does not equal 0. And you say, well, why do we have to include that? Well, if we look here, if q of c is 0, then you have divide by 0, and then we're going to get an error. This is a big one for what we're going to be studying later on in one of the next videos, is when you have rational functions. So we have to make sure this denominator is not 0. Then we can just rewrite it like this. Okay, so here's our example. Find the limit of, as x approaches 1, of x squared plus x plus 2 all over x plus 1. So I'm going to put in 1 here, and 1 here, and now I can evaluate. 1 squared is 1, plus 1 is 2, plus 2 is 4, over 1 plus 1 is 2, and I get 4 over 2, which is just 2. Alright, so notice how the denominator did not equal 0, so I could just evaluate it just like it is. So it's a lot just like evaluating. Put in this number in for every one for x that you see. Alright, and here this theorem 1.4 is kind of the same thing. I want to just go over the definition, which is kind of the important part, not anything else, because it's pretty straightforward. But it says, the limit of a function involving a radical. Let n be a positive integer. The following limit is valid for all c if n is odd, and it's valid for c is greater than 0 if n is even. So let's just look at just this odd part first. So if c is odd, that means right here, if I have an odd function, if this number is, if n is odd, I can do this for anything. A negative number, then take the cube root, you're going to get an answer. Alright, so remember just how cubic functions work. I can take the cube root of a negative number, right? Negative 4, I can get an answer, and take the cube root to go backwards. Alright, so it works out. If c is got to be greater than 0 because it's even, remember, even functions are the ones that look more like that. So we're not going to be, if c is negative, it's going to be down here somewhere, and I can't take like the square root of a negative number. So that's not going to work. So if c is even, or if n is even, c has to be greater than 0, so we can kind of have an answer. Otherwise, we get no solution. If n is odd, then it doesn't matter what c is. You'll get an answer. Alright? Good. Here is the next one. Theorem 1.5. The limit of a composition function. If f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches L of f of x is going to equal f of L. So we put in this L into the f function, and then you would evaluate, just like you would for a composition function. And then what you would get is the limit as x approaches c of f of g of x equals f of L. So here's an example. The limit as x approaches 0 of the square root of x squared plus 4. So what we're going to do is we're going to just take this, the inside function, that's like our g of x, and we're going to put it over here. So we say, what's the limit as x approaches 0 of x squared plus 4? Well, 0 squared, 0 plus 4 is 4. And I take that, and I'm going to say, okay, now I'm going to say, what's the limit as x approaches 4 of the square root of x? So I'd say that is the square root of 4, which is 2. And I know what you're saying, but Mr. Bartman, can't I just plug in 0 and figure out what's going on? Yes, you could do that also. Plug in 0 for x squared, you get 0 squared plus 4, you get 4, and then take the square root, and you get 2. That's what we did, just showing you in different steps what it might look like. Alright, and I do believe this is the last. Yes, it is. Here is the last theorem. Theorem 1.6. Limits of trig functions. Let c be a real number in the domain of the given trig function. So remember, sometimes like where that tangent function goes, you know, that tangent goes like this. It just keeps on repeating itself. So at this one spot, we're not going to have any values because there's an asymptote. So it would be, as long as it's in the domain, you're going to be okay. The limit of as x approaches c of sine x equals sine c. Limit as x approaches c of cosine x equals cosine c. Limit of x approaches c of tangent x equals tan c, and the same for the co-functions. I'll just leave this up for a second so you can pause, you can see it. Okay, good. I'm glad you wrote all that down and you paused it. So now let's go to the answer to your trivia question. What did competitive eaters munch on at a 2004 Madison Square Garden event called the Battle to the Bone? The correct answer, of course, is buffalo wings. If you said chicken wings, I'd accept that also. Alright, thank you very much for watching. See ya.